What's the time?
It's time for Maths with Mr. Thomas.
Here we go, Chapter 10, Lesson number 12, the review lesson. We've made it to the end, high five, of a Gaussian Elimination and Matrices. This is a review lesson. It doesn't include anything new. It's just a summary of everything from this chapter. It's just me going over it quickly and highlighting the key points. If there's anything you're unsure of, or you want more of an explanation, you want to see more examples, look back at the individual lessons where I will explain everything in a little more detail. So we started this chapter off looking at Gaussian elimination. Woo! What is Gaussian elimination? Well, that's just an algorithm which allows us to solve n equations and n unknowns. So the majority of the time we would have 3 equations and 3 unknowns, or x, or y, and or z. How do we solve it? Well, we set up an augmented matrix, then we perform a series of row operations to reduce the matrix to upper triangular form. Remember, that's when each entry below the leading diagonal is 0, and then we can use backward substitution to solve. For example, if we have these 3 equations, these 3 unknowns, x, y, and z, we can set them up as an augmented matrix. So we take the coefficients of x, y, z, and we take whatever that is equal to, and we would have row 1, row 2, and row 3. First thing we do is we change these 2 entries to 0, and we do that using the row 2 and row 1, or this one you use row 3 and row 1. So you can say row 2 take away row 1, so you do that. First row will stay as it is, and the second row, row 2, will go to row 2 take away row 1. So 1 take away 1, 3 take away 2, 1 take away 3, and then 3 take away 12. For row 3 to get that to 0, well, you take away double row 1. So row 3 will go to row 3 take away 2, row 1, and you do that. After you have these 2 entries as 0, you change this one to 0, but you have to do that just using row 2 and row 3. If you don't use just row 2 and row 3, these entries will change, which you don't want. You need to keep the zeros here, so you can say then that if you do 1 take away 1, so in other words row 3 take away row 2, that will give you 0. So doing that, it gives you this triangle of zeros here, and once you have that, what you can do is use backward substitution. So you're going to take this coefficient of z and say negative 2z equals negative 8 and solve for z. After that, go up a row, woo, to row 2. And you can say 1y take away 2z equals negative 9. You know what z is, so you can sub that in and you can solve for y. And after that, you go up another row, woo, to row 1, and you can say 1x, add 2y, add 3z equals 12, sub in the values of both y and z, because you found them here, and it lets you find the value of x. After you have found the value of x, y, and z, you can have a party. Other examples, very, very similar, but it's far better to start these questions with Gaussian elimination if the first entry in the first row is 1, so you can change the order of the equations. It just makes it slightly easier. So we're going to put this equation just first, and then we're going to put this one second, and we're just leaving the third one as it is. You're doing the exact same thing. Again, you want your triangle of zeros. First thing you do is you take these entries to 0 using row 1. So you can say that row 2 take away 2, row 1, and you can say row 3 take away 4, row 1 will give you the zeros. If you do that, you have your zeros here, woo, and you need to change this entry to 0 as well. You do that again using just row 2 and row 3. Do not use row 1, otherwise this entry will change here. You need to keep these 2 entries as 0. So you can say row 3 add on 10, row 2 would give you the 0 here. Once again, you've got your triangle of zeros, upper triangular form, so you can use your backward substitution. So 45z equals negative 90, solve for z. After you know that, you can go up a row, woo, and you can say 1y add on 4z equals negative 9 and solve for y, because you're just subbing that value of z in here. And after that, you go up another row, woo, and you can say 1x add on 2y take away z equals 3, sub in the values of x and y, and it lets you find out x as well. Once you've done that, you can say x is this, y is this, z is this, and once again, have a party. Lesson 2, we were looking at Gaussian elimination again, but we were looking at special cases. Woo! So your special cases. A lot of the time when you use Gaussian elimination to solve your equations, you will end up with a unique solution. In other words, you will end up with your little triangle of zeros here, ain't it pretty? And you can solve for your z, your y, and your x. However, this is not always the case. You always have to think as well about redundancy, inconsistency, and ill-conditioning. What is redundancy? Well, if you are using your Gaussian elimination and you end up with a row of zeros, well, this row of zeros ends up telling you absolutely nothing. It is useless. It becomes redundant. And if you end up with this, then it means your system of equations lack a unique solution. And it means that there will be infinitely many solutions because this row is redundant, you cannot use it, and you would use this row. But if you think about this row, if you have something y at something z equals something, well, there's infinitely many solutions for that. So if you end up with your row of zeros, then it's redundant, and it means there's infinitely many solutions. Inconsistency. If you end up with a row of zeros apart from what the value would be equal to. So if you have 0x, 0y, 0z, and that equals some number apart from 0, well, that makes no sense. You can't have 0x add 0y add 0z equals, for example, 7. It makes no sense. Mamma mia, what does that mean? Well, it means that there are no solutions. You cannot have that, so it is inconsistent. Ill-conditioning, what is this? Well, that's when there's a small change in either the right-hand side or a coefficient of x or y, and that triggers a large change in the overall solution. So here you can see you've got x 333y, and that's 343. 3x add 1000, y equals 1030. So x is 10 and y is 1. If though you add 4 onto this value, so we've done that. Well, how does that change your solution? Well, it means then that the value of x now goes to negative 1322 and the value of y is 5. So you can see that just a small change to one of these values, we've just added 4 here, and that has resulted in a massive change in the overall solution. And that is what is meant by ill conditioning. So, the 3 things you need to look out for. Redundancy, when you get your row of zeros, it means there's infinitely many solutions. Inconsistency, if you get your row of zeros apart from this last value. And ill conditioning, when a small change in either a coefficient or the right hand side leads to a dramatic change in the overall solution. And obviously, most of the time, it really helps if you just get your unique solution with your little triangle of zeros. After Gaussian elimination, we then went on to look at matrices in a little more depth. So a matrix is a rectangular array of numbers. A matrix with m rows and n columns is said to have order m by n, or m times n. So this here, you can see there are 2 rows and there are 3 columns, so that'll be a 2 by 3 matrix. Each number in here is known as an entry or an element, and if you're wanting to take, for example, matrix A, and you have 1, 3, then it means the first row and the third entry. So you will have negative 1. If you have, for example, the same number of rows and columns, it's known as a square matrix. This matrix here, C, is known as a column matrix because there's just 1 column. And this matrix here is known as a row matrix because it's just 1 row. Equal matrices, how are matrices equal? They are equal if and only if the entries, the corresponding entries, are the same. So if 2x was equal to 6, if 0 is equal to 0, if negative 1 is equal to negative 1, and x and y is equal to 1. So matrices are only equal if they're of the same order and all pairs of corresponding entries are the same. If they are, then you may get problems such as this. Note that because the order of these matrices are not equal, they are not equal matrices. We then looked at addition and subtraction of matrices. How do we add and subtract? Well, all you do is, if the order is the same, you just add the corresponding entries. So you would have the 3, add on the 2. You would have the 4, add the negative 1, and the 5, add the 2. And the negative 2, add 3, and you get the idea. Simple as that. It's the same with subtraction. You do the 5, take away 1, the 1 take away negative 2, the negative 2 take away 2, blah, 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 blah. Scalar multiplication. If you're multiplying your matrix by a scalar, just a number, what you do is you multiply every single element, every entry by that scalar. So you'd have the 3 times the 2, the 3 times the 1, the 3 times the negative 3, the 3 times the 5. Woo! And you get out your answer. Transpose of a matrix. That is when you swap the rows for the columns. So the first row, the 3, 4, 5, becomes the first column. The second row will become the second column. That is the transpose, and you write it as A dash. Note, if matrix A is of the order m by n, for example 2 by 3, then the transpose of matrix A will be of order n by m. So that will swap round the rows and the columns, and that will become a 3 by 2. If you take the transpose of a transpose, you get back to matrix A. And if you add matrices and then take the transpose, that's the same as taking the transpose and then adding them. And if you multiply by a scalar, then take the transpose, that is the same as taking the transpose and multiplying by the scalar. Symmetric and skew-symmetric matrices. A matrix is symmetric if the transpose is equal to A. So if you swap the rows for the columns, so that first row becomes the first column. The second row becomes the second column. The third row becomes the third column. If you end up just back with the matrix that you had at the start, the matrix is said to be symmetric. What's meant by skew-symmetric? Skew-symmetric. Well, that is when you take the first row and it becomes the first column, the second row and it becomes the second column, and so on. But if you end up with the negative of what you had at the start, so you can see here that really A, the transpose of A, is the negative of A, and that means the matrix A is going to be skew-symmetric. After that, we looked at matrix multiplication. So in the first lesson of matrices here, we were multiplying by a scalar, but you can also multiply a matrix by a matrix. Yeah, show me more. Okay, so in order to multiply matrices together, you have to look at the order. A matrix product AB can only be formed if the number of columns of matrix A is the same as the number of rows of B. So if A is of the order m by n and B is of the order n by p, this number in the middle, the n and the n, has to be the same. The resulting matrix will be m by p. So some examples of that. This matrix here, matrix P, is a 2 by 2 matrix. This matrix Q is a 2 by 3 matrix. Because the number in the middle is the same, woo, you can multiply them together. And the resulting matrix will be of order 2 by 3. How do you do this? How do you multiply them? Well, you know you're going to get out a 2 by 3 matrix. To work out this entry, which is in the first row in the first column, you multiply the first row of the first matrix by the first column of the second matrix. So you do 4 times 2, add on 3 times 6. To work out this entry here, which is in the first row in the second column, multiply the first row by the second column. So 4 times 4, add on 3 times 1. For this entry here, which is in the first row in the third column, you multiply the first row by the third column. So 4 times 5, add 3 times negative 2. You want to keep going with that. This entry here is on the second row and the first column, so you multiply the second row by the first column. So negative 1 times 2, add on 2 times 6. This entry here is in the second row in the second column, so you multiply the second row by the second column. So negative 1 times 4, add on 2 times 1. And this entry, which is in the second row in the third column, you multiply the second row by the third column. So negative 1 times 5, add on 2 times negative 2. You can work that out and you will end up with a result. Note, you cannot multiply matrix Q by matrix P. You cannot have Q times P because Q is a 2 by 3 matrix, P is a 2 by 2 matrix, and the numbers here in the middle are not the same. Bum, bum, bum. So you cannot multiply them together. So the order is very important. After that, we went on to look at the identity matrix. And the identity matrix, matrix I, is just this. It's when you have a leading diagonal of 1s and the other entries are just 0. So this here is the 2 by 2 identity matrix. If you have a general matrix with entries A, B, C, D, and you multiply by the identity matrix, either the identity matrix times A or A times your identity matrix, you just get out A. Which means then that if you multiply a matrix by the identity matrix, you just get that original matrix. So really it's just like multiplying by the number 1. So your identity matrix behaves just like the number 1. The 3 by 3 identity matrix, well, it's the same thing. You've got a leading diagonal of 1s and all the other entries are 0s, and it behaves the exact same way. Looking at some examples of that, well, given the 2 by 2 matrix A, find the values of integers p and q such that a squared equals pa plus qi. Well, for this to work out a squared, well, you know you were multiplying those matrices together. That's a 2 by 2, that's a 2 by 2, 2 and 2, you can multiply them together, and the result would be a 2 by 2. For pa plus qi, well, p times matrix A plus q times matrix I. Remember, I is your identity matrix. You can work out that. You can multiply by the scalar and then you can add. And for that, because it says they are equal, well, you're just going to equate the entries. So you'd have 1 equal to the 2p plus q. You'd have negative 7 equal to the negative p. You'd have 21 equal to 3p. And using that information, you can solve to find the values of p and q. This part here is quite common. It says, hence express the matrix A cubed in the form of xa plus yi, where x and y are integers. Because we just worked out that a squared equals 7a, take away 13i, well, if you want to work out a cubed, that's when you would multiply your a squared by another matrix A. So you'd have matrix A times this 7a, take away 13i. For that, if you multiply out the brackets, so you'd have 7a squared take away 13ai, and remember ai is just equal to a. What you want to do with that is, well, you know a squared is equal to the 7a take away 13i, so you can sub that in. Then using some algebra, multiply that out, so 7 times 7a will give you 49a. 7 times 13i will give you the 91i, and you'd be taking away the 13a. From there, you put the a's together and the i's together, and then you can work out the coefficients of a and I. We then looked at the determinant of a square matrix. What is the determinant of a square matrix? Well, that's just a number that is associated with that matrix, and it's written as det A or A with these lines either side. So the determinant of a 2 by 2 matrix, you can work that out by calculating A times D take away B times C. So the determinant of matrix A, written either way you like, is going to be A times D take away B times C. We looked at some examples. So the determinant of this matrix, you would have 2 times 4 take away 1 times 3. For this one here, you'd have 3 times 1 take away 2 times negative 2. Ta-da! That's it. The determinant of a 3 by 3 matrix, slightly trickier. What you have to do for that one is you would take that first entry in the first row and you would have 1 times, and then you would eliminate its row and its column, and you'd work out the determinant of this remaining matrix. So negative 2 times 1, take away 3 times 1. You would then repeat that for the second entry in the top row. So you'd have 2 times, eliminate its row and its column, and you're left with a 4, 3, 2, negative 1. So work out the determinant of that. And then finally, take the third entry in that top row, and you'd have 1 times, eliminate the row, eliminate the column, and you're left with this matrix here. So work out the determinant of that. We went on to look at that. So as I said, you would have 1 times, eliminate the row, eliminate the column. So you'd have the determinant of the negative 2, 3, 1, negative 1. So just work that out. Then you would take that second entry, the 2, and you're multiplying that by, eliminate the row with the column, and you've got the 4, 3, 2, negative 1. And finally, taking the 1, and eliminate the row in the column. So it's 1 times, eliminate that, and it's a determinant of this matrix here. When you do that, you're going to have a plus, minus, plus pattern. So this will be positive, then you'll be taking away something, and then you will be adding. Make sure you pay attention to that. After that, we went on to look at the inverse of a matrix. So if you think about these two matrices here, A and B, if you multiply them together, so A times B or B times A, you get out the identity matrix. Because of that, you can say that matrix B is known as the inverse of matrix A, because when you multiply them together, you end up with your identity matrix. The inverse of matrix A is denoted, it's written as A to the power of -1. This means the inverse of matrix A. It's only square matrices that have an inverse. Oh yes, but not all of them, and it all comes down to the determinant. If the determinant is not 0, then it means an inverse exists, so A to the -1 exists, and you would say that the matrix is invertible, so you can find the inverse, or non-singular. It means then that the inverse of matrix A is such that if you have matrix A and you multiply it by its inverse, you will get out I. Or if you multiply the inverse by matrix A again, you get I. On the other hand, if the determinant of a square matrix is 0, well, what does that mean? No inverse! Perfect, there is no inverse, and the matrix is said to be non-invertible, or singular. Sometimes an inverse matrix can be found from a given matrix equation. So if you can get the equation down to A times something equals I, well, that something is going to be the inverse. So if the determinant is equal to 0, then it means the matrix is non-invertible or singular. And if the determinant is not equal to 0, then you can find the inverse. It's invertible or non-singular. So some examples, this one here, let A be this matrix, show that this matrix is invertible. What does that mean? Well, it means the determinant must be 0, so show that. So the determinant, you would have the 2 times 3, take away the 4 times 1, that is 2. This determinant is not 0, so it means that an inverse exists. So since the determinant is not 0, matrix A is invertible. For part B, show that A squared equals 5A take away 2I. Well, that's similar to what we did before. You'd have matrix A times matrix A. 5A take away 2I is 5 times matrix A. It's 2 times your identity matrix, multiplied by the scalar, subtract the corresponding entries. Ta-da! And you have shown that A squared equals the 5A take away 2I. Well done. Part C, hence obtain the inverse matrix A to the -1. Remember, if we can write our equation as A times something equals I, then that something has to be the inverse of matrix A. So we need to rewrite our equation, this A squared equals 5A take away 2I, in the form of A times something equals I. To do this, we're subtracting 5A from both sides, but on the other side it leaves us with -2I. So multiply through by -1, and it means this -5A will become 5A. This A squared will become -A squared, and this -2I becomes 2I. From there, take out A as a common factor, so it's going to be A times 5, but we can't just have A times a number, we have to write it as a matrix. So 5 you can write as 5I, because remember, A times I is equal to A. So we can have A times 5I. We've got A times the A, which gives us the A squared, and that's equal to 2I. Because we've got A out as a common factor, well, we need to get that as A times something equals I. So divide both sides by 2. So you've got half over here now, and it's A times the half, 5I take away A. And that half of 5I take away A is what we're multiplying A by in order to get your identity matrix. So it means the inverse of matrix A is just that half of 5I take away A. And you could then go on and work that out. So 5 times your identity matrix, taking away matrix A, multiply by the scalar, subtract the corresponding entries, and then we can find 5I take away A. And all you have to do is just half each of the entries in order to get the inverse. Woo! After that, we went on to look more closely at the inverse of a 2 by 2 matrix, and what we found was that there's a quick way of working it out. Woo! What you can do if you're given the general 2 by 2 matrix A, so the entries A, B, C, and D, what you can do is if you work out 1 over the determinant, so A times D, take away B times C, and if you multiply that by the matrix, but you swap A and D around, and you take the negative of whatever B and C are. That will give you the inverse. So the inverse of matrix A, the quick way of doing it is work out 1 over the determinant, swap A and D around, and take the negative of whatever B and C are. We did that here with this example, find the inverse of matrix A. First of all, we need to know, how do we know an inverse exists? Well, remember, an inverse exists if the determinant is not equal to 0. So the determinant will be 2 times 11, take away 3 times 7, which gives us 1. 1? Yes, which means that it's not equal to 0, so an inverse exists. To find the inverse, we have 1 over the determinant, so it's 1 over 1, and then all we do is we swap the 2 and the 11 around, and we take the negative of the 3 and the 7. 1 over 1 is just 1, so multiply through by 1, well, it's just staying as that, 11 negative 3, negative 7, 2. After that, we looked at the inverse of a 3 by 3 matrix. This was slightly trickier, and if you want me to go through it in more detail, look back at that lesson. To find the inverse of a 3 by 3 matrix, you have to use your identity matrix. So you set up your augmented matrix with your matrix A, and then beside it your identity matrix, and then you use your Gaussian elimination, so your row operations, in order to change the identity matrix from being on the right hand side to being on the left hand side. As I said, look back at that lesson if you are wanting more detail. So using Gaussian elimination, you can start to change the left hand side into your identity matrix. You're starting off just the same way, get these two entries to 0. Once you've done that, get this entry to 0 as well, so you get your little triangle of zeros. After you've done that though, you also need to change these entries to 0 as well. So again, you're going to continue with your row operations. So we've got our triangle of zeros, and we're going to make this a 0 as well. After that, we'll make both of these equal to 0, and then it's just this one we need to change. Once you've done that, what you should get down to is all zeros here and zeros here. And this leading diagonal, you need to make all the entries 1. So to do that, you divide the top row by 5, divide everything there, and that gives you the 1. The second row, divide everything by negative 5, that gives you again the 1. And the bottom row, just multiply through by negative 1, and it gives you the 1 there. So you can see that you now have the identity matrix on the left hand side with the leading diagonal of 1 and all the other entries 0. What you end up with on the right hand side is the inverse of matrix A. Woo! That is how it is done. We then went on to look at transformation matrices. What was that all about? Well, let's say you've got point P, which has the coordinates 2, 1. Position vector P, so the distance from the origin, if you're thinking about that as a vector, you could write that as 2, 1 as a vector. But remember, column vectors or position vectors, they're just in 2D 2 by 1 matrices. So that point there represents the vector P. If we apply a transformation, what we're doing is we're applying that to that position vector. And what we do is we multiply our position vector by a 2 by 2 transformation matrix. So let's say we had this transformation matrix here with the entries 2, 1, negative 1, 2. What we can do is we can multiply them together. So a transformation matrix multiplied by matrix P. This here was a 2 by 2 matrix, this here was a 2 by 1 matrix. Always check the numbers in the middle are the same, which they are. Woo! Means you can multiply them. The result will be a 2 by 1 matrix. We get out 5, 0, and really what we have out is another position vector. But if we think about that as a coordinate, well, that's just going to be the coordinate 5, 0. So what we've done is we've gone from this first point to the second, and we've done that using a transformation matrix. A transformation matrix is just a 2 by 2 matrix that can alter a point in the Cartesian or your xy plane. Remember, the result of a transformation of xy is written as x dash y dash, and is known as the image of that original point. So if a transformation t maps point xy onto the image point, you can write down that t maps xy onto the image point x dash y dash. Really, to transform a point using a transformation matrix, you multiply two matrices together. So you write the point as a point matrix, xy, and you multiply it by the transformation matrix. However, the order is important. You have to multiply the transformation matrix. First of all, you write that first, and then multiply it by the point matrix. What you will get out is the image point matrix. We looked at this example here, so find where this transformation matrix maps the point -3, 1. So, transformation matrix multiplied by the point matrix equals the image point matrix. Just remember, transformation matrix is first, so we've got the 5, -2, -1, 3, and we're multiplying that by the -3, 1. We know this is a 2 by 2 matrix, 2 by 2. We know this is a 2 by 1 matrix, 2 by 1. Always check the numbers in the middle are the same, which they are, woo! And the result will be a 2 by 1 matrix. To work out this entry here, which is in the first row in the first column, multiply the first row by the first column. To work out the next entry, so this entry here, which is in the second row in the first column, multiply the second row by the first column. That gives you -17, 6, which means then that -3, 1 maps to the image point, -17, 6, if you write that as a coordinate. That there was a random transformation, but there are standard ones that you needed to know, and this is them there. So reflections in the x-axis, the y-axis, the line y equals x, rotations of 90 degrees and 180 degrees about the origin, and rotations of any angle about the origin. We also need to look at dilation, which is an enlargement or reduction, or compositions of all of the above, which we looked at in the last lesson. Just remember to work this out. So if we're looking at a reflection in the x-axis, we would have a point P which has an x-coordinate and a y-coordinate. If we reflect that in the x-axis, well, the x value will remain as it is. The y value will become the negative of whatever y is. So we would end up with an image point P which has x and then negative y. So we can write down x and then negative y. What we can do is we can write both of these, the x and the negative y, in terms of x and y. So x you can write as 1x plus 0y, and negative y you can write as 0x take away 1y. If you take just the coefficients, well, you've got 1 and 0, and you've got 0 and -1. You can easily check that if you multiply this matrix by the matrix x and then y, well, you get out x negative y, which means the matrix associated with a reflection in the x-axis is this one. It's the 1, 0, 0, -1. Reflection in the y-axis, you're just doing the same thing. Start with a point P, so you've got x and then y, and if you reflect that over, well, you'd have the negative over whatever x is, and the y value would stay the same. Write that out as a point matrix, so you've got negative x and then y, and write it down in terms of x and y. So negative x you can write as negative x add 0y. Y you can write as 0x add 1y. Take the coefficients, -1, 0, 0, 1, and you can easily check that if you multiply this matrix by the point matrix xy, you get out negative xy. So it means then that this is the matrix associated with reflection in the y-axis. Rotation of 180 degrees about the origin, so a point P with the coordinates x, y, well, if you rotate that round or reflect it in the origin, you will get out the negative x and the negative of y. So negative x, negative y, you can write as negative 1x, add 0y, 0x take away 1y. Take the coefficients, once again, -1, 0, 0, -1, check that if you multiply them, that is what you get, which it is, and it means that's the matrix associated with a rotation of 180 degrees. Reflection in the line y equals x. So if you had this point 5, 3, if you reflect that in the line y equals x, well, your 5, 3 would go to 3, 5. So really, just the x and the y would swap about. If you write down the image point as a point matrix, so we've got y then x, write it again in terms of x and y. So that's 0x add y. That's 1x add 0y. Take the coefficients, and from there, check if you multiply them, you do get y and an x, which you do. So it means this matrix here is the matrix associated with reflection in the line y equals x. Woo! Other one you need to know is dilation. So if you've got point P, which has the coordinates x and y, if you're using a scale factor of 2 and you're using the origin as the center of the dilation, then what you can do is you can say that that point would map to, well, you would double it, so you'd have 2x and then 2y. Write down the 2x, 2y as a point matrix. Again, write it in terms of x and y. Take the coefficients, so 2, 0, 0 and 2, multiplying that by the original, xy, you can check that you do get 2x and 2y. The matrix associated with that then is the 2, 0, 0, 2. Really, whatever your scale factor is, so if your scale factor was some other value, let's just say k, then the matrix associated would be k, 0, 0, k. So if your scale factor was 5, you would have 5, 0, and then 0, 5. Other ones you need to know or be able to work out, well, a rotation of 90 degrees, that's when you would have your original point, x, y, and that would move to negative y, and then x. Write down the negative y, x, do the same thing, write it in terms of x and y, take the coefficients, multiply by x, y to check that you get that, and that is the result that you would have. That's the matrix that would be associated. Rotation of any angle about the origin, so it's not always going to be 180 degrees or 90 degrees, you might have say 30 degrees or anything at all. First thing you need to think is that when you're rotating a point about the origin, it's always to be done in an anti-clockwise direction. Anti-clockwise! To do that, you would use this matrix here, which has the entries cos theta, negative sine theta, cos theta, and theta is going to be the size of the angle that you're rotating it through. So, a summary, these are all the transformations that you need to know. Again, if you want more detail, look back to that lesson, where I'll also have some examples. Just look out for the likes of this question here. So write down the 2 by 2 matrix associated with a clockwise rotation of 30 degrees. Just make sure this question says clockwise! But you know it's always got to be an anti-clockwise rotation. So a clockwise rotation of 30 degrees would be 360, take away 30 gives you 330. So that would be an anti-clockwise rotation of 330. Using that matrix, cos theta, negative sine theta, cos theta, sub in the anti-clockwise angle of 330 degrees, and you end up with this matrix here. So that's the matrix that would be associated with a clockwise rotation of the 30 degrees. Finally, we looked at a composition of transformations. What is all that about? Well, that's when you want to combine some of your transformations. However, remember when you multiply matrices together, the order is important. Matrix A times matrix B is not the same result as matrix B times matrix A a lot of the time. So the order is very important. If you apply a transformation B to A times X, well, that would have to come first, the way you write it. So you always have the second transformation multiplied by the first transformation. So if the first transformation was A, if you're applying that to your point matrix, and then you apply a transformation B, well, you have to multiply them in reverse order. So it would be B times A times X. So it's the second transformation multiplied by the first, and then multiply that by the point matrix if you need to. For example, with this here, find the image of the point AB under reflection in the x-axis, followed by reflection in the line y equals x. Well, this is going to be the matrix that's associated with reflection in the x-axis. This one here will be reflection in the line y equals x, but when you multiply them together to apply that to a point, you do it in reverse order. So find the image of the point under reflection in the x-axis. So this one here is first, then the line y equals x, so this one's here is second, but when you multiply them, you would have the second one, so the 0, 1, 1, 0, multiplied by the first, so the 1, 0, 0, negative 1. Multiply that by AB, and then this is what you would end up with. So you can say then that the image of AB will go to negative BA after those transformations. That there is a summary of everything you need from the lessons. If you need any more of an explanation, look back at the individual lessons. Good luck. Woo! Matrices is finished. High five!